You ever just look at a leaf? Like, really look at it after a rainstorm? You might not realize it, but you're actually staring at the most advanced energy technology on the planet. It's so easy to take nature for granted, right? But when scientists actually try to replicate what a plant does effortlessly, turning sunlight and water into stored chemical energy, they hit this absolute brick wall of incredibly complex solid-state physics. Today, we're exploring that massive gap between the elegant, almost quiet magic of a natural leaf and the brutal, highly precise quantum engineering we humans require to actually copy it in a lab. Welcome to This Explainer. I am absolutely thrilled to guide you through this fascinating deep dive today. We're going to completely unpack the entire story of artificial photosynthesis. We'll trace the journey from understanding those incredible biological miracles happening right out in your backyard to translating those exact mechanisms into solid-state physics, semiconductors, and nanomaterials. It's essentially this epic story of human ingenuity trying to steal nature's oldest secret to build a truly sustainable energy future for us all. So here is the roadmap for our macro to micro journey today. Number 1, nature's biological blueprint. Number 2, the quantum engineering challenge. 3, the Z-scheme solution. 4, modeling charge dynamics. And 5, formulating solar fuels. Let's get right into it. Section 1, nature's biological blueprint. The original solar plant. Before we can even think about building our own synthetic systems, we really need to examine the highly efficient biological machinery that scientists have been desperately trying to steal secrets from for decades. I mean, for billions of years, plants have operated as flawless, self-sustaining solar plants. A lush forest isn't just scenery. Actually, think of it more like a massive, silent factory. Plants don't need highly toxic batteries or spinning turbines. They just spread out their leaves, wait for the sun to rise, and let biology do the heavy lifting to power their entire existence. It's incredible. Okay, let's dive right into this governing chemical reaction that makes literally all of life possible. It looks pretty simple on the surface, right? You've got 6 molecules of carbon dioxide and 6 molecules of water, and when they're powered by a photon of light, that's the HV you see right there, they transform into sugar and 6 molecules of oxygen. The plant is literally taking the exhaust of our breath, mixing it with rain, and using sunlight to forge solid, high-energy fuel. And it gives us back breathable oxygen as a mere byproduct. Now, to really understand how we can engineer this ourselves, we have to break this overwhelming biological process down. It's basically 3 crucial steps. Whether it's happening inside a leaf or inside a high-tech photoelectrochemical cell, these rules apply. Step 1, you must absorb a photon of light. Step 2, you must separate the electrical charges that photon creates. And step 3, you must use those separated charges to drive a chemical reaction and actually form your fuel. If we zoom way, way down into the molecular level of a leaf, we find nature's ultimate catalyst for this whole process. It's called the oxygen evolving complex. This delicate little cluster of manganese and calcium incredibly manages the charges, step by step. As light hits the system, it cycles through different oxidation states, from S0 all the way through S4, accumulating the exact amount of positive charge needed to physically rip water molecules apart. It is an absolute masterpiece of nanoscale engineering, and it's exactly what scientists are trying to mimic with synthetic catalysts today. Section 2, the quantum engineering challenge, racing against time. Shifting our narrative from biology to physics, well, this is where we hit a massive roadblock. When we try to mimic nature using artificial semiconductors, we face a really unique challenge. So when sunlight hits our synthetic material, we need it to absorb the energy and kick an electron up across what's called a band gap, jumping from the valence band up to the conduction band. This creates an excited electron and leaves behind a positively charged hole. We want to use those separated charges to drive our water-splitting reactions right at the surface. But here is the terrifying timing dilemma. Once we excite that electron across the band gap, physics desperately wants it to fall right back down and recombine with the hole. And that recombination, it happens in a blistering 1 to 10 nanoseconds. But the actual chemical cycle required to split water and make fuel, that needs a whole millisecond to complete. So we are 1,000,000 times too slow. We are essentially racing against time at the quantum level. And the stakes of losing that race are, well, absolute destruction. If we fail to manage this timing perfectly, the uncontrolled energy forms destructive radicals. These highly reactive species essentially tear the system apart from the inside out, destroying the delicate materials before any useful chemical reaction can even occur. We don't just lose efficiency here, we lose the whole machine. Section 3, the Z-scheme solution. Dividing to conquer. To overcome this massive timing and recombination roadblock, engineers had to come up with a brilliant architectural workaround known as the Z-scheme. Look at the difference here. On the top left, a single component system struggles because the electron and hole are just too close together. Their wave functions overlap, and they recombine instantly. But on the bottom right, the Z-scheme physically separates the reduction site and the oxidation site into two entirely different semiconductor particles. By dividing the labor and keeping the charges physically separated via an electron mediator, we drop that wave function overlap straight to zero. We basically buy ourselves the time we need.
What's really amazing here is that human engineers didn't actually invent this trick. Nature did. Biology figured out this dual system separated structure billions of years ago. Natural photosynthesis utilizes two distinct photosystems, P680 and P700, linked together to step the energy up twice, forming a Z shape on an energy diagram. We are literally copying nature's architectural blueprints to fix the flaws in our solid-state physics. How cool is that?
Section 4, Modeling Charge Dynamics, the math behind the magic.
Because in the lab, we can't just plant a seed and watch it grow, right? We have to calculate the precise behavior of electrons. To evaluate how charges will behave at the exact junction between our semiconductor and the water, engineers rely on the Mott-Schottky equation. Now, don't let the complex math intimidate you. Just think of this strictly as a translator. It helps us calculate the built-in electrical potential of our material. That's basically the invisible force field that helps push the excited electrons and holes apart so they can actually do useful work. To ground this math in physical design, let's just look at the variables really quickly. Engineers can actively tune the Na and Nd, those are the doping concentrations, meaning they intentionally add specific impurities to the semiconductor. And by changing the doping, they control W, the depletion width. It's essentially the fine art of sculpting the internal electrical landscape of a crystal to guide charges exactly where we want them to go. Once the charges are moving, we absolutely must track them. Enter the continuity equation. Think of this as the ultimate accounting ledger for a semiconductor. It allows engineers to calculate the exact rate of charge accumulation over time and space within the material. If we want a steady, reliable flow of solar fuel, this equation needs to balance perfectly. Translating this calculus into real-world physical actions gives us a super clear picture. The total rate of charges we collect equals the rate we generate them with sunlight, minus the ones lost to recombination, plus the ones spreading out via diffusion, and influenced by their drift in the electric field. It's this intricate, beautiful balancing act that engineers absolutely must optimize to make artificial photosynthesis viable. We can anchor this complex math visually right here. Imagine a cross-section of our solid-state material. As a green photon strikes the surface, it generates a charge pair. The equation we just looked at maps out exactly how those holes physically move, scatter, and drift through the block. Understanding this three-dimensional dance is literally the only way we can design better, more efficient photoelectrodes. Section 5, Formulating Solar Fuels, Closing the Loop. So, after all the complex modeling and nanoscale engineering, what is the ultimate goal of all this? It's creating usable, storable, totally clean energy. When we successfully manage the photon absorption, prevent that pesky recombination, and channel our charges to the surface catalysts, we achieve water splitting. Two molecules of water are broken down to yield oxygen gas and our ultimate prize, hydrogen gas. This is a 100% clean, carbon-neutral fuel generated directly from abundant water and free sunlight. It is, without a doubt, the holy grail of future energy sustainability. But as we look toward this incredible future, I want to leave you with this profound thought. Even a change of a fraction of a nanometer causes the wave to die. It reminds us just how fragile and precise this quantum balance truly is. Nature makes it look incredibly easy, but building our own sustainable energy future requires a mastery of the universe at its smallest possible scales. Can we perfectly engineer that fraction of a nanometer to save our planet? Well, that is the question driving the next era of science. Thank you so much for exploring this with me today.